Yeah, moving on to the third chapter of Module 4 of microcontroller and an embedded system. This topic is all about hardware, software, co-design and programming model. So whatever we have studied in the previous class, those were all the subunits what we have studied, or we were actually looking into if there is an embedded system, how basically an embedded system is going to look like, or what are the different parts of an embedded system. Right now in chapter 3, that is about hardware, software, co-design and modeling, we are going to check how basically these ECUs are manufactured, or how basically the embedded systems are manufactured. That is what we are going to look into. As I told you in the very previous sessions, embedded system is nothing but a combination of hardware as well as software. In case of your embedded system, we'll be calling them by the name firmware. So it is basically the combination of hardware and software together. So in this particular chapter, we need to check out how basically a hardware is manufactured and how basically a software will be manufactured, and how the both will be combined together in order to bring out a single product which is called as embedded system for a particular application. That is what we are going to study in this particular topic. Moving on further. For example, if we speak about the old traditional days when there was no much competition in the market, what people used to do was, or what the manufacturing companies used to do was, they used to manufacture hardware units separately and the software units separately. Which what I mean to say is, there were separate hardware developers and there were separate software developers. So the hardware developers would study what are the system requirements, and based on the system requirements they would manufacture this particular hardware components, and after the hardware components are being manufactured, next task would be given to the software manufacturer. So the software manufacturer would basically be looking into what are the system requirements, and he would manufacture the software corresponding to the embedded system. Finally, they would integrate hardware and software together and they would come out with the product, or finally they would come out with the embedded system. So this is what that was happening in the old traditional days. But nowadays, what problem would have happened, or what was the problem that was existing because of the old traditional days was, as I said you, nowadays time, we studied in yesterday's class, time to prototype and market. Time to prototype and market is comparatively very small. So you cannot ask a hardware designer to hardware a hardware component, and you cannot ask a software designer to design a software component, and you cannot combine them, which means that you are not allowed to waste lot of time in developing your product. If you are going to develop a lot of, or if you are going to waste a lot of time in developing the product, normally what happens is, maybe there will be some other competitor who would bring his product to the market and you ultimately would be losing the market. So what they do nowadays, or what this embedded system manufacturers do nowadays, is they co-design hardware and software together. So they do not have a segregation between hardware and software. They basically will be manufacturing the hardware and software components together, and finally they would come out with a single product which would actually be reducing the time to prototype and market. That is what it is given here. See here, in the traditional embedded system development approach, the hardware software partitioning is done at the early stage, and engineers from the software group would take care of software architecture development, and the engineers would take care of the hardware development. There is no interaction between both of them. Between the software team and between the hardware team, there will be no interaction at all. Once they come out with the hardware and software requirements, and once they are built up with the hardware and the software of an embedded system, finally they would combine them together, or finally they would integrate it together. But why this particular method has been discarded is because of the increasing competition in the commercial market and the time needed, or a need to reduce the time to market. So keeping this in mind, they came with a novel approach. So what is this novel approach? Novel approach is nothing but software and hardware components are co-developed together, and whenever they felt that there should be a segregation that should be happening between the both, they segregated it. So that is how it is happening nowadays. So whatever we have studied here, this is with respect to the traditional day, and whatever it is happening right now, this is all about a co-design process where hardware and software are combined together just to make sure that your product comes to the market in very short period of time and you get a sufficient time to make your product grow in the market. Okay. How basically this is done, or what are the basic issues that normally the embedded system manufacturer would actually face in the co-design process? So what they will do is, first of all, they will go to the consumer and they would get the requirements. They would ask the consumer, what are your requirements? And the requirements, whatever they are going to get, will be called as system requirements or functional requirements. Once this functional or system requirements are obtained, this is converted into maybe this is converted into functional prototypes, or they are converted into functional prototypes. And once they are converted into functional prototypes, they are simulated. And once the simulation has been done, the manufacturer will come to know which should be kept as a hardware part and which component should be made out of software, or what should be written in terms of code and what should be actually the mechanical parts. So here basically they'll be segregating, that is at the end of the manufacturing process they'll be segregating between the hardware and the software components. This is how it actually happens. But when they are segregating, or when they are manufacturing the components together, or when they are going with the co-design process, they will be facing lot of issues. So initial thing what we need to know here is we need to check out what are the fundamental issues a embedded system designer is going to face when he is going to design hardware and software together. So basically that is what we are going to look into in this particular session of the class. So the hardware software co-designer, or the hardware software co-design, is a problem statement, and when they actually try to solve this problem statement in real life, they may come across multiple issues in the design. That is what I said. It is easy to go to the consumer, it is easy to get the functional or system requirements, and it is easy to simulate it. But once it is simulated, you are not going to know what are the actual issues you are going to face. You will come to know what are the actual issues only when you try to implement it. So when you try to actually implement this particular product, then you are going to face the actual issues that, or the embedded system manufacturer will be facing the actual issues, and those actual issues or those fundamental issues are the ones what we are going to check out in today's session. So check out. The following section illustrates some of the fundamental issues in the hardware software co-design. So when you are going to mix up the things together, there are a lot of issues what normally an embedded system manufacturer will say. Theoretically speaking, I'll say, yeah, it is easy to design a hardware and software together. But practically when you're going to do it, it is not that easy. There are a lot of issues what you're going to face. The first issue is about selection of the model. Which model are you going to select? There are multiple models which are existing in the market, and you should make sure which model you are going to select in order to bring out the product. And this is again a difficult task, because once you select a model and once you start implementing your product, at a particular stage of implementation, your product or the model whatever you selected will become non-functional. It will not be functioning at all. Then what you have to do is you have to switch between the models. You have to take some other model which will be overcoming the disadvantages what you had in the previous model, and you should actually start implementing your system requirement on that particular new model. So selecting the model is one of the difficult tasks, and this is going to take lot of time. After that, selecting the architecture. So once you are done with the selection of the model, you should actually go with the implementation, which you should actually go with the actual manufacturing. So you should check out what is the architecture I am going to select in order to come out with the original product. So that is all about selecting the architecture. In fact, we are going to study this in detail one by one. We are going to study this, don't worry. Finally, selecting the language. So this both are with respect to hardware, okay? This both are with respect to hardware. So once you are done with the hardware implementation, you need to check out what are the different software components that are needed for the product, and you should also know what is the type of the language you are going to use in order to make that particular product functional or efficient or totally functional or 100% functional. Finally, after you are done with the language selection and coding, then you are going with the partitioning the system requirements in the hardware and software. Finally, you are going to say, fine, this is my hardware component and this is my software component. Up till here, you were not saying which is hardware and which is software. Because if you have designed a hardware component here, for the hardware to work efficiently, you would have needed some software codes, right? So normally you will be manufacturing the hardware and software components together when you are going with the embedded system manufacturing, and later you will be segregating it. You will be saying that fine, this is what is my hardware component and this is what is my software component. This is regarding the design process. Now basically what you are trying to do here is you are actually trying to develop a prototype. You are not going to bring the product to market. You are going to develop a prototype, and once your prototype is ready, you are going to segregate which is hardware and which is software. Now if you know what is hardware component and software component, now you can ask the vendors to manufacture the hardware and software separately and you can combine them. But initially during the design process of your new product, you cannot have a segregation between the hardware and software. So these are the four important issues what a normal designer or a manufacturer of an embedded system will be facing. Fine, moving on further, we need to check out what basically is this model, how are you going to select the model, what are the different architectures, what are the different ways in which the architecture can be selected, what are the different languages you can write your code in, and how basically the partition will be happening. So first thing, selecting the model. As I said you, in the hardware software co-design, models are used for capturing and describing the system characteristics. So what exactly it means is, it is actually a dummy model. Dummy model in the sense, you know what are your requirements, you know what are your characteristics, you know what are your attributes. You are going to develop a system which will be having all the properties and all the characteristics what actually a consumer has asked you. So that is what it is. So model is all about it's a formal system which will be consisting of objects and composition rules. Objects and composition rules means various components which will be behaving as per the requirements of the consumer. It is hard to make a decision on which model should be followed in a particular system design. As I said you, it is not an easy task to select a model. Most often, designers switch between varieties of models from the requirement specification to the implementation aspect of the system design. So they might take model 1 and they might start with the implementation. Once they are done with the implementation 1, or once they are done with the once they start implementing the model, they might find this to be responsive. It may not be responding to the requirements at all. Then they will switch to the second model. Even the second model, when they go to around 30% or 40% of the implementation, this will also become irresponsive. Then they might go to the third model. So normally the manufacturer will not stick on to the very initial model, whatever he is going to take. He is going to switch between the models as per the requirements. See, here is given there, the example is given. At the specification stage, stage means a stage where the embedded system manufacturer would go to the consumer and ask what are your requirements. He knows only the functionality of the system. He knows what are the requirements of the system, but actually how it is implemented is not known to him. So normally what he does is he will be selecting one model and he will try to bring out all the functionalities what a consumer says. But when he starts implementing the actual functionalities, this will become irresponsive and he need to go with the higher model. So this is what is selection of the model. Selecting the models means it is all about how you know. For example, if I say that, let's say that you do not know which mobile phone to buy, okay? Simple example. So what you will buy is you will normally go with a mobile phone which is of 2 GB, 16 GB. But once you start actually working on that particular mobile phone, you feel that memory is not enough and the speed is not enough. So what you will do? You will go with the 3 GB, 32 GB. Then after that, once you are very well versed with this particular model, what you will do? What you will feel is this is also not enough. You will go with 464 or you will go with 128 GB. So this is what is meant by selecting the models. So initially they will take the very basic one and they will try to implement all the functionalities in that particular model. If it is not going to work out, they will go to the higher model and they will try to implement the functionality. This is all about the microprocessor or microcontroller what I am speaking about, okay? So whenever I say it's an embedded system, it is all about a combination of a sensor and actuators and a microcontroller. So normally, as per the requirements, you will take some sensors, you will take some microcontroller and you will take the actuators. Once you feel that the embedded system whatever you have developed or embedded system whatever you are simulating, actually you are simulating here, whatever you are simulating is not responding as per your requirement, then normally you will go to the higher version of the microcontroller. You will say I want an 8-bit one, you will say I want a 16-bit one, you will say I want a sensor which is much more faster, you will say I want an actuator which is actually working much more faster than the previous thing. That is what is meant by selecting the model. Moving on to the next thing, that is selecting the architecture. So once you are done with the simulation part, once you know that which microprocessor to take and which sensors to take and which actuators to take, right now you need to go with the implementation part. A model only captures the system characteristics and do not provide information on how the system can be manufactured. So previously you had only a model, a normal model which would have been written in terms of some language or some code or something, and you came to know that it was working very fine. Now what you try to do is you actually try to implement it. It is just like sitting in a simulator of a driving class and driving a car. You will come to know the actual issues when you are stuck in a traffic or when you are stuck in a uphill. Once you are in a simulator, you will not come to know. A simulator will only tell you how the gear has to be changed, how the accelerator, brake, clutch has to be applied, and how the steering has to be used. But the actual thing will come into picture only when you are driving a car in a actual traffic or in a uphill. That is what it is saying here. Selecting the architecture. Once you are selecting the architecture here, the embedded system manufacturer will face the actual issues. Even though his model was working very fine, but when it comes to the actual implementation, he has to take a lot of difficulties or he'll be facing a lot of problems. The architecture specifies how a system is going to be implemented in terms of the number and types of the different components and interconnections among them. Quite enough. You should take a microcontroller in real, you should take sensors in real, you should take actuators in real, you should take user interfaces in real, and you should start working on that. So when you start working on that, then you are going to face the actual issues. When you are selecting the architecture, there are a lot of architectures what can be selected by the embedded system manufacturer in order to manufacture a product. Some of the architectures are given here. One is called as control architecture. We are going to study this architectures one by one. Data path architecture, CISC architecture, RISC architecture, VLIW, very long instruction word computing architecture, single instruction multiple data SMID architecture, multiple instruction multiple data architecture are the very commonly used ones in the system design based on the requirements. So if you're asking me, sir, which one I'm going to take, you can take the things as per your requirements. But before taking the architectures here, you should make sure what is your requirement, how are you going to implement it, and how it actually has to function. If that is known to you, and if you know what are this particular architectures, then you can make a selection between which architecture suits you the best. Some of the applications or some of the architectures here are like application specific. Application specific means, for example, if I speak about CISC architecture, this architecture will work fine only if there are instructions which are complex instruction set, which means that which are comparatively bigger instructions. CISC means it is all about a single instruction but a bigger instruction, but these instructions are going to do multiple tasks in a single one. Are you getting this? For example, you want to compare the data, add the data, and you want to subtract the data, and you want to store the data somewhere. 4 functions has to be performed. So if that 4 functions has to be performed, then you can use a simple single instruction, and that instruction is called as complex instruction set. Whereas in case of your reduced instruction set computer, one instruction can do only one task. Whereas complex instruction set computers, a single instruction can do multiple tasks. So that is what it is all about. So that is what it says here. Some are application specific, while some are general purpose. General purpose means any applications you say, any embedded systems you say, you can go with the any of the architectures. For example, here controller architecture is a application specific. This architecture can be used only in case if you want to design some control units. Whereas when I speak about the CISC and RISC architectures, you can use it in order to manufacture the what you can call the control unit as well as the sensors or as well as the connection that happens between the sensors and the actuators. That is what architecture means. So basically what you have done is you have come out with the dummy model and your model is working fine. Now you have to implement this model into reality. You have to bring this model into reality. When you are bringing this model into reality, there will be a lot of difficulties what you are going to face. This is something like that is happening in case of your how you did in your lab last year. For example, if I go with analog and analog circuits, you had some 3 circuits to be implemented using some software, right? So there you used to get the output very easily if your circuit is fine. But when you actually implemented the circuit in reality, you never used to get the input because there were some issues what you are facing. Very similar to that, model means it is something which has happened in the software. They have just developed a model. They just wanted to see whether it works fine. When you bring that model into reality in the actual environment, you will face the issues. So when you are facing the issues, you need to sort it out. So that is what is the selecting the architecture all about. Let's check out what are this architecture. Control architecture implements the finite state machine model using a state register and 2 combinational circuits. So basically what happens is, let us say that you want to implement something like x is equal to a plus b, okay? So this will be a one state, this is b second state, this should go together and this is the addition that is happening and finally you will come out with x. So this can be called as your finite state machine things. In fact, there is a lot more difference between what I have written here and what actually it is. So control architecture implements the finite state machine model using state register and 2 combinational circuits. State register holds the present value and the combinational circuits implements the logic for the next state and the output. So this can be called as control architecture. This can be called as controller architecture, where you have the present state or where you have got the state registers and the combinational circuit. Combinational circuit is nothing but a circuit which will be doing the arithmetical or logical operations. That is what is your control architecture. In fact, control architecture is application specific, okay? You need to know what is the application you are going to do and based on that you are going to go with the architecture. Data path architecture is all about, that is also very similar to your controller architecture itself, but that is best suited for implementing the data flow graph model. In fact, you would have studied all these particular things. DFGM you would have studied, where the output is generated as a result of predefined computations of the input data. So it is something like this. A will be here, B will be here, addition happens here, this will be X, this is Y, this is C here, so C here, this is going back here, this is minus. So Y is actually X minus C, X is equal to A plus B. So that is your data path architecture. Data path architecture represents the channel between the input and output. But the inputs, whatever you are going to give here, are the predefined inputs. And the data path architecture will also contain registers to contain the data, counters, register files, memories and ports along with the high-speed arithmetic units and the other control units. So this is compared to the complicated one compared to the controller architecture. So basically this is how you actually go with the real-time implementation. Finite state machine data path. This finite state machine data path is actually the combination of 2 things whatever I studied. It actually consists of a control architecture and the data path architecture. Controller architecture will be helping or it will be generating the control unit, whereas the data path will be processing the data. The data path contains 2 types of input ports, out of which one acts as a control port and the second acts as a input output port for the data to flow inside. So if you combine the first and second one together, you get something called as finite state machine data path. I do not think they will be asking any theory with respect to this. They will have some problems to be asked with respect to this. So you will come to know a lot about this particular controller architecture, data path architecture or FSMD architecture when you actually take the models and when you actually try to sort the issues. So this is second architecture which can be implemented. Third one is complex instruction set architecture. Complex instruction set architecture is you write a single instruction and the single instruction is able to do multiple tasks. It is possible for the RISC instruction to set to perform a large complex instruction operation with a single instruction. That is, you want to compare, you want to add, you want to negate and finally you want to jump. So maybe you can use the instruction JNCE, which is a complex instruction set which will be doing all this particular task in a single instruction. But the problem with this particular CISC architecture is normally the CISC architecture will be taking lot of taking lot of time for the execution of a single instruction because it's a 32-bit or 128-bit or bigger instruction, right? But it will be consuming lesser space. It will be consuming lesser space. That is what it says. However, it requires an additional silicon for implementing microcode decoder for decoding the CISC instruction. The data path for CISC processor is complex. So that is all about this complex instruction set architecture, which means that you are going to write you are going to implement your model using instructions. You are going to write a program, and the instructions what you are going to write are CISC instructions. So if you have got a bigger model, you can implement that particular bigger model using minimum instructions. That is what is your CISC architecture. Reduced instruction set architecture is all about uh, let me say that you have a CISC architecture here, okay, for a particular model, which is written using some 8-9 lines. Suppose if you want to implement the same model into reality using the RISC architecture, then this might go for somewhere around 10 to 20 lines, where every instruction is going to do a single operation, whereas here a single instruction was performing a multiple operation. In case of this instruction, the time taken to execute one single instruction will be very less, but whereas the memory required in order to store all this particular instruction is comparatively very much more. That is what is your RISC architecture. The very long instruction word architecture implements multiple functional units in the data path. That is, this is A, this is B, it has to be added, then it has to be compared, then it has to be negated, then it has to be like stored somewhere. So in the data path, before the output comes, in the data path there will be multiple functionalities to be executed. This particular architecture is called as very long instruction word architecture. That is what happens here. The VLIW instruction package, one standard instruction per functional unit of the data path. That is what this VLIW architecture is all about. Parallel processing architecture. Parallel processing architecture is all about implementing concurrent processing elements, and each processing element may associate a data path containing register and a local memory. Let's understand this. Parallel processing architecture means it is about let's say that there is a data here, okay? There are multiple datas here. And there is a single instruction which is written here. One instruction. So you want this instruction to be working on all this particular data that is present here, and that will happen parallelly. That is what is called a single instruction multiple data. See here, in single instruction multiple architecture, a single instruction is executed in parallel with the help of processing element. The scheduling of the instruction execution and controlling of each what you can call this processing element is performed through single controller. The SMID architecture forms the basis of reconfigurable processors, which means that you have a single operation to be performed in an architecture. Maybe let's say that you have an addition to be performed here, and you have multiple data to be added up. So what you do is you write a single instruction, and those single instructions will be working on this particular data parallelly. But it will consume time, no issues. Whereas in case of your multiple instruction, multiple data architectures, you have multiple data here and multiple operations to be performed. In case of your multiple instruction, multiple data architectures, they execute one instruction at a time, second instruction at the second time, third one at third, fourth one at fourth, which means that the time consumed here will be comparatively more because different instructions to be performed, right? So you need to check whether your for example, let us say that you have to rotate your stepper motor in the clockwise direction. So rotating your stepper motor in the clockwise direction is a single task, right? So what you can do is you can go with the SIMD architecture or SIMD architecture, where a single operation can be performed multiple times because it is all about rotating the stepper motor, right? For example, if I say that you have to rotate 2 steps clockwise and 1 step anti-clockwise and again 2 steps anti-clockwise, which are multiple operations, then you can go with the multiple instruction, multiple data architecture. So if you have got a same operation to be performed, then you can go with the SMID architecture. If you have got multiple operations to be performed on the multiple data, then you can go with the MIMD architecture. So that is what is MIMD, and that is about parallel processing architecture problem. Selecting the language. So this is the third issue. So whatever we have studied till now, that is control architecture, data path architecture, FSMD architecture, CISC architecture, RISC architecture, VLIW architecture, PP architecture. All these are with respect to the selection of architectures where we are actually implementing the model into reality using any one of this architecture. So based on your requirements and based on the way in which your system is going to work, you can select any one of this architecture, or you might go with the multiple architecture also. After the architecture has been selected, you need to know what is the language in which you are actually going to write the program in. That is, you are speaking about the software things here. You are actually going to check out which program, which language you are going to check, and there is no hard and fast rule for that. Okay, you can take any of the things. You can write it using C, you can write it C++, or C hash, Java. You can go with the VHDL, System C, Verilog. Any of the languages can be taken by you people or taken by the manufacturer depending on us flexibility with the language what is known to him. So he can go with any of the languages. There are no issues with respect to the languages what he has to take in order to implement the software part of the model or software part of the project or software part of the embedded system what has to be brought into reality. Final problem is partitioning system requirement into hardware and software. So this is actually one of the difficult tasks here. You have the hardware part, you have the software part. Right now you have to segregate what is the hardware part and what is the software part. And there are various trade-offs that happens. There are various disadvantages when you are trying to segregate between the hardware and the software part, or when you are trying to partition between the hardware and the software. There are various issues what you are going to look into. In fact, the trade-offs between the hardware and the software partitioning will be studied as an entirely different chapter which we are not going to look into. So right now what we have done is we have just glanced what are the normal issues a embedded system manufacturer will face when he has to bring the system requirement into reality, bring the consumer requirements into reality. That is what is about this particular concept. Moving on further, that is with respect to the computational models in embedded design. This is where what I said, we are going to study about all the data flow graphs or FSMD models in detail with respect to the numericals. So this particular title will be giving you regarding the various computational models which will be built by the embedded system designer when he is actually designing a embedded system. So there are different computational models what can be used. Just like the various architectures what you have taken into account, you can take or you can design or you can go with the various computational models. Out of them, some are given here. First one is called as data flow graph model, DFG model. Second one is control data flow graph model, state machine model, sequential program model, concurrent or communicating process model, or object oriented model. So the very commonly used models in order to develop. We spoke about selecting the models, right? We spoke about selecting the models. This is what it is all about. These are the different models what comes into picture when we are actually starting with the design part. So we need to check up what are these particular models. Let's check up the first one. Data flow graph bar diagram model, which we normally call it as DFG model. The DFG model translates the data processing requirements into the data flow graph. To be very frank enough, if I speak about a lot of theory here, you people are not going to get anything because you will not understand anything if I tell the theory part with respect to this particular model. But still, we'll go with the minute of the minute details of this particular model. The data flow graph model is data driven model in which a program execution is determined by the data. This model emphasizes on the data and the operation on the data transform the data input or input data to the output. So how actually this is going to look like. So if you want to look how this is going to look like, this is how it is going to look like. So DFG model, you'll be having the data here. So these are all the data. A is data, B is data. This is a operation that is happening on the data, and this is the output. So I can consider A is an input, B is an input, and this is a data flow node where both are added together and you get one output, that is X. That X is added or it is brought to one more data flow node where it is subtracted from the other one, and finally you get the output. This particular model is called as data flow model. So you basically will be knowing what are the inputs that comes to the system and what should happen with the input that are coming to the system and what are the internal operations that should be happening with the system. Just like how you write a logical operation or logical equation, you write something like a plus b uh, odd with, or this is I mean odd and ANDed with c and d, right? So you know what should be happening. If I ask you to write this particular things, you will take the this things here, you will take the things and you will write it down here, right? So this is what is your data flow model. Data flow model actually tells you what are the inputs and what are the outputs and what are the intermediate outputs. That is what has been explained here. Data flow graph is a visual model in which operation on the data is represented using a block and the data flow is represented using our arrows. Inward arrow to the process represents input data and outward arrow from the process represents output data. Embedded applications which are computational intensive and data driven are modeled using DFG model. See, data coming inside, going out, again that is coming inside. So this is your DFG model. This particular model can also be called as acyclic DFG, where it doesn't contain multiple values of input variables or there are no multiple outputs. So you can call this as acyclic one. Moving on to the next one, control data flow graph model. Control data graph model is very similar to the data flow graph model itself, except a condition being added. There is a condition added. So if the condition is satisfied, then it is true. If the condition is not satisfied, then it is false. That is what is your control data flow graph model. For example, take here the condition. If flag is equal to 1, x is equal to a plus b, else y is equal to a minus b. So if you plot it, then it is like this. Data comes inside, a and b comes, or condition is checked whether the flag is equal to 1. If the flag is equal to 1, then a and b are added together and that comes as the output. If flag is not equal to 1, if it is false, then a and b, a minus b will happen and that will come to the output. So this is what is your control data flow graph model. Normally this is what happens. You see, the control data flow graph model is used for modeling applications involving conditional program execution. CDFG models contain both data operations and control operations. Control operation is this one, okay? This is your control operation and this is your data operation. Because it has got both control unit and the data flow nodes together, you call this particular model as CDFG model. So if your program gets executed based on the condition, then you can go with the CDFG model. If there are no conditions to be satisfied in your model, then you can go with the normal DFG model. The next things what we need to check out, we will check out in the next session of the video. Thank you.